Welcome to the deep dive. Okay, picture this. You're looking through a telescope, right? And you see two stars side by side. They look like they're, dancing together.
They look like a pair.
Exactly. But how do you know? How do you, as an astronomer, prove they're actually orbiting each other, truly linked by gravity, and not just, well, one star way behind the other, just lined up by chance?
That really is the core challenge, isn't it? Distinguishing a real physical binary system from what we call an asterism, just a chance alignment in our line of sight.
Right.
And our sources today, they lay it all out. We're going deep into how astronomers actually confirm these true binaries and how they measure the properties of some really extreme objects involved, like neutron stars, even exoplanets.
Okay, so the key isn't just looking. It's about finding the physical evidence, the proof.
Precisely. It all comes down to detecting and measuring the effects of gravitational binding and orbital motion.
Yeah.
If you can measure that mutual tug.
Then you've confirmed the link. Makes sense.
Exactly. And we've got three main methods to cover today. They range from, well, pretty subtle measurements of nearby stars, all the way to spotting these massive cosmic smash-ups millions of light years away.
All right, let's start with the light then. How do astronomers pick up that wobble signature you mentioned, the one that proves two stars are really connected?
Well, the basic idea is that in any binary system, nothing's truly standing still. Both objects orbit a common center of mass, or COM.
Ah, right. Even the bigger star moves a bit.
Yep. If one's much heavier, the COM is closer to it, sure. But the smaller object still pulls the massive one around in a little orbit, causing a wobble.
And we spot that wobble using the Doppler effect. That's where the light comes in.
Exactly. As the star we can see gets pulled towards us by its unseen partner, its light waves get squished slightly shorter, shifting towards the blue end of the spectrum.
Blue shifted.
And then, as it swings away from us in its orbit, the light waves get stretched out, longer, shifting towards the red.
Red shifted. Got it.
That repeating spectral shift is the money shot. The proof is tracking that periodic, regular Doppler shift. If you see that red-blue pattern repeating consistently over time, could be days, months, years.
Then you know something's orbiting it. Like with Sigma Sagittarii, the source is mentioned using the gravity instrument for that one.
Precisely. Instruments like gravity are designed to track that subtle periodic movement with incredible accuracy.
Now, I saw in the sources that this radial velocity method, it only gives us the companion's minimum mass. It mentioned 1 sin I Nargo. Why is that little term so important? What's the catch?
Yes, nunner tari darter. That's sin I part highlights the method's main limitation. We only measure the velocity along our line of sight. We don't usually know the inclination of the orbit, like how tilted the system is relative to us.
Okay, so if we're looking at it face on.
If its face-on inclination is 0 degrees, sin I is 0, and we see no radial velocity wobble at all, even if there's companion. If its edge-on inclination is 90 degrees, sin I is 1, and we measure the true velocity and can get the true mass.
But usually it's somewhere in between.
Usually, yeah. So the velocity we measure is only a fraction of the true orbital velocity. That means the mass we calculate is only a minimum mass. The real mass could be higher.
Right, unless we can figure out that inclination angle somehow.
Exactly. But even just getting that minimum mass is super useful. It helps us tell the difference between, say, a really small dim star and a big gas giant planet. Our sources note that if the minimum mass consistently comes out lower than about 10 times Jupiter's mass, it's very likely a planet.
Okay, that makes sense. So moving from optical wobbles to listening, the second proof uses pulsars, nature's best clocks.
That's right. Pulsars are these rapidly spinning neutron stars, incredibly dense remnants of massive stars. They sweep beams of radio waves across space like a lighthouse.
And the pulses are super regular.
Extremely regular,
Yeah.
so precise they rival atomic clocks.
Wow, and if that pulsar is in a binary system?
Astronomers can use those ultra-precise timings. Deviations in the pulse arrival times tell us about the pulsar's orbit, its location, and crucially, the mass of its companion, even if the companion is totally dark, like another neutron star or black hole.
How does that work exactly? How does timing tell you mass?
This is where Einstein comes in general relativity. If the pulsar's signal has to pass near its massive companion on its way to us, the companion's gravity literally warps space-time around it.
Okay.
That warped space-time means the radio signal has to travel a slightly longer path. It gets delayed, just a tiny bit, but measurably so.
A little cosmic detour.
Kinda, yeah. It's called the Shapiro delay. Measuring that specific, predictable delay is direct proof of the companion's mass. It confirms the gravitational link. We saw this with PSR J05134002E, for example.
That's incredible, a delay in radio waves confirming a black hole's mass.
It's powerful stuff.
Yeah.
And that leads us to the third proof, the most, well, definitive one for the really heavy hitters, gravitational waves.
Ripples in space-time itself.
Yeah.
This is for the most extreme binaries, right? Neutron stars or black holes actually merging.
Exactly. Things we often can't see any other way, especially at vast distances, when detectors like LIGO and Virgo pick up a signal.
How do they know it's real, not just, a truck driving by or something?
Well, they're incredibly sensitive, so filtering noise is a huge challenge. But confirming a real astrophysical event involves a couple of key things. First, the signal has to match the theoretical models predicted by general relativity. It's called waveform matching.
So they compared the detected ripple pattern to a library of predicted patterns from merging black holes or neutron stars.
Pretty much, yeah. They have complex models for what the signal should look like depending on the masses, spins, and so on.
And the other key thing.
Multiple detectors.
Yeah.
The signal must show up in detectors hundreds or thousands of miles apart, like a LIGO Hanford in Washington State and a LIGO Livingston in Louisiana. And crucially, it has to arrive with the correct time delay between them.
Based on the speed of light, or rather the speed of gravity.
Exactly. For GW150914, that first black hole merger detection, the delay between Hanford and Livingston was just 7 milliseconds.
Tiny.
Tiny, but precisely what you'd expect for a wave traveling at the speed of light across that distance. That rules out local noise.
And the statistics. I saw a mind-blowing number for GW150914.
Oh yeah. The statistical significance has to be enormous. For GW150914, the chance that a signal that strong and that well-matched to the models was just random detector noise was calculated to be less than once in 200,000 years.
Wow, okay. More than 5 sigma, as they say.
That's the gold standard. So you have the waveform match, the multi-detector confirmation with the right time delay, and the overwhelming statistics. That's how you confirm these incredibly distant, violent binary events.
So whether it's a star wobbling nearby or black holes merging billions of light years away, the proof always comes back to measuring the physical effects of their mutual gravity. No measurable effect, it's probably just an asterism, especially if other checks, like parallax, show they're at totally different distances.
You got it. That's the core principle.
Okay, so we've confirmed they're bound together. But how far away are these things? The scales must be immense.
They really are. I mean, take a relatively well-known system, the neutron star-white dwarf binary PSR 1620 plus 26, that's about 12,400 light years away.
Which sounds like a lot, but it's practically in our galactic neighborhood, isn't it, compared to the gravitational wave events?
Oh, absolutely.
Yeah.
GW170817, that first binary neutron star merger we detected, that was 40 megaparsecs away.
40 megaparsecs. Remind me, how big is a megaparsec?
1 megaparsec, or MPC, is about 3.26 million light years. So 40 MPC is roughly 130 million light years away.
Okay. Wow, how on earth do we measure distances like that accurately?
Well, for the nearby stuff, like pulsars within our galaxy, we can sometimes use pulsar parallax.
Like stellar parallax, measuring the apparent shift against background objects as Earth orbits the sun?
Exactly the same principle. Because we know the size of Earth's orbit very accurately, we can measure the tiny angular shift, the wobble, of the pulsar over 6 months. Trigonometry then gives us the distance. We often use networks of radio telescopes, VLBI, to get the super precise angular measurements needed.
But 130 million light years. Earth's orbit isn't going to cut it for parallax there. So for the GW events.
For those, we rely on the gravitational wave signal itself. It's called GW triangulation. Remember that time delay between detectors?
Yeah, the 7 milliseconds for GW150914.
Right. By measuring the precise arrival time differences at multiple detectors spread across the globe, LIGO, Virgo in Italy, now Korea in Japan, we can narrow down the direction the wave came from.
Like how our ears figure out where a sound is coming from based on tiny time differences.
It's a very similar idea, yeah. And the amplitude, or strength, of the signal also contains distance information. Stronger signal generally means closer. So combining timing and amplitude lets us estimate both the location on the sky and the distance.
That localization must be crucial, because it leads to the ultimate confirmation, right? Multi-messenger observation.
Yes. That's the holy grail. Seeing the same event with completely different kinds of telescopes, gravitational waves and electromagnetic waves, like light, radio, X-rays.
And GW170817 was the breakthrough for that.
It absolutely was.
Yeah.
The gravitational wave detection went out, pinpointing a region of the sky, And almost immediately within seconds for some signals, hours and days for others, telescopes around the world swung into action.
The sources said over 70 observatories.
Yeah, an incredible coordinated effort. They caught the kilonova, the celestial light show, the radioactive glow from the debris flung out by the merging neutron stars. Seeing both the GWs and the light from the same event, that provided ironclad confirmation and helped nail down the location and distance with amazing accuracy.
Just incredible. Validating our ability to measure these extreme events across cosmic history.
Okay, so we know they're bound. We know how far away they are. But what about figuring out what the objects themselves are like? Especially the really weird ones, neutron stars and exoplanets. Both push the limits of our physics and our measurement tech.
Let's tackle neutron stars first.
Hmm.
You called them extreme laboratories. What are the big mysteries we're still grappling with?
Two main ones stand out. First is the fundamental unknown equation of state, or EOS.
The EOS. That dictates how matter behaves inside the star, right, under those insane pressures and densities.
Exactly. It governs the star's structure, its size, how squishy it is. But the problem is, the density inside a neutron star crushing the mass of the sun into something the size of a city is so extreme we cannot replicate those conditions in labs on Earth.
So we can't directly test our theories of matter at that density.
Nope. We have theoretical models, lots of them, but we don't know which one accurately describes what's really going on inside. It's a major unsolved problem in nuclear physics and astrophysics.
Okay, that's a big one. What's the second challenge? The mass gap.
Right. This is kind of an observational puzzle. We see neutron stars typically up to about, 2, maybe 2.2 times the mass of the sun, and we see black holes starting around 5 solar masses. But that region in between, roughly 2 to 5 solar masses, we don't see many objects there.
Huh. Why not? Is there a reason objects can't form there, or is it just hard to tell them apart?
That's the debate. Is there a real physical gap, or is it just really difficult to distinguish between the absolute heaviest neutron star right before it collapses into a black hole and the absolute lightest black hole? The physics in that transition zone is really murky.
So how are gravitational waves helping chip away at these problems? You mentioned the EOs earlier.
Right. GWs from merging neutron stars give us a unique probe. Just before they merge, the intense gravity of each star stretches and deforms the other. We call this titled deformability.
How much they get squished.
Exactly. A star made of stiffer matter, a different EOS, will deform less than a softer star. We can actually measure this effect in the gravitational wave signal in the final moments before the merger.
Ah, so the GW signal tells you how squishy the neutron stars were.
Precisely. And that measurement directly constrains the ES. It lets us rule out theoretical models that predict stars that are too stiff or too soft compared to what we observe. It's an indirect way to probe that extreme physics.
That's clever. Using space-time ripples to study subatomic physics. And we're getting faster at analyzing this data. Ding GW150914.
Yeah, that's a really exciting development using machine learning. GW150914 can analyze a binary neutron star signal and estimate all 17 key parameters, masses, spins, tidal deformability, location, etc., in about 1 second.
1 second. Seriously? Compared to what?
Compared to potentially hours or even days with traditional methods, that speed is absolutely critical for getting alerts out to optical and radio telescopes for that crucial multi-messenger follow-up we talk about. Finding the light show requires knowing where to look fast.
Game changer. Any other ways we're probing neutron stars?
Well, looking ahead, giant new ground-based telescopes like the ELT, the Extremely Large Telescope, might be able to detect the faint infrared glow from old isolated neutron stars, possibly picking up reheating effects that could also give clues about their internal structure and cooling processes.
Okay, let's switch gears to exoplanets. Using that radial velocity method, the wobble, we still face big challenges finding Earth-like planets, don't we?
We absolutely do. We still have the NRF-Zendelar problem only getting the minimum mass, which can make it hard to be sure if something is a massive planet or a tiny star if we don't know the inclination.
Right.
But honestly, the biggest hurdle for finding true Earth analogs, small rocky planets in the habitable zone, is stellar noise.
Noise from the star itself. How does that work?
The star isn't perfectly quiet. It has things like rotating star spots, like sunspots, plages, bright active regions, convection bubbling up on the surface.
Yeah.
All these things cause slight variations in the starlight and can create Doppler shifts that look like the signal of a small planet.
So the star's own activity mimics the signal we're searching for.
Exactly. And it's not a small effect. For a star like our sun, this jitter or noise adds up to about 50 centimeters per second of scatter in the velocity measurements.
50 centimeters. And the signal from an Earth-like planet.
We expect that to be tiny, around 9 centimeters per second, maybe even less.
Wow. So the noise is 5 times bigger than the signal. You're trying to hear a whisper in a noisy room.
That's a great analogy. It's incredibly challenging.
So how are astronomers tackling this, pushing the precision?
It's been an ongoing technological race. The HARPS spectrograph was revolutionary, achieving about 50 centimeters precision, good enough for Neptune-mass planets. The current generation, like Espresso on the VLT, is pushing towards 10 centimeters,
Getting closer to Earth mass?
getting there. And future instruments, like Codex proposed for the ELT, are aiming for an astonishing 1 centimeters precision.
1 centimeter per second. How is that even possible? The stability must be insane.
It requires heroic engineering. To eliminate tiny instrumental drifts that could mimic a signal, these modern spectrographs are incredibly stabilized. They often use clever techniques like simultaneously observing a reference source. And the instruments themselves are housed in temperature-controlled, pressure-stabilized vacuum vessels.
Sealed off from the world.
Pretty much. Isolated from almost any environmental changes, temperature swings, pressure changes, even vibrations.
And the calibration, how do you make sure your wavelength measurement is that precise?
That's been another huge leap. The cutting edge is using laser frequency combs.
Laser cones.
Yeah, think of it as a perfect optical ruler. It produces a spectrum of light with thousands of precisely spaced, ultra-stable lines or frequencies. Astronomers use this comb to calibrate the spectrograph with unprecedented accuracy. It's the key technology enabling that push below 10 centimeters, maybe even reaching that 1 centimeters goal.
So incredible stabilization plus perfect calibration. That's the path to finding true Earth twins. Hashtag tag tag outro.
It really is amazing when you step back, whether we're watching a nearby star do a tiny wobble,
Or timing a pulsar's delay across galactic distances.
or decoding the ripples from black holes colliding billions of years ago.
It all comes back to measuring the effects of mutual gravity. That's how we map the universe and its contents.
And these methods aren't just finding things, they're actually helping us solve fundamental physics problems, Using GWs to test the neutron star EOS, building instruments precise enough to finally overcome stellar noise and find Earth-like planets.
It really feels like we're pushing boundaries on multiple fronts. And that speed aspect you mentioned, Dingo BNS getting 17 parameters in 1 second.
Yeah, that speed, combined with the precision we're achieving.
It makes you wonder, doesn't it? With that kind of rapid analysis and AI assistance, are we getting close to a future where we can actually observe every major binary merger across the whole electromagnetic spectrum almost the instant it happens? A real-time cosmic alert system.
That's the dream, isn't it? That ability to react instantly, globally, that's shaping the next decade of discovery. It's an exciting time.
Definitely something to think about. Until next time on The Deep Dive.